Today on Engine Power, we're building a bullet that'll make more horsepower than any naturally aspirated engine we've ever had in the shop. When we're done with it, this Big Block Chevy will power XOR's over-the-top Willys Wagon.
Welcome to Engine Power. Today we are going to embark on an engine build that is a true race piece, and it will make more naturally aspirated horsepower than we have ever made before. The more power you make, the stronger the engine you need. So it's important to start with a solid foundation. This short block is the creation of Blueprint Engines, and it's made right here in the USA. It's a Big Block Chevy that's available in both standard and tall deck heights. Since we're looking for maximum displacement, we opted for the tall deck. Another thing that will increase the displacement is the finished bore size of 4,600, drastically larger than a stock Big Block Chevy. The included forged steel crankshaft has a stroke of 4,750, which gives us 632 cubic inches. You have seen us run Blueprint engines in the past, and it's for good reason. They're well designed, reliable, and they're perfect for someone who wants to save the time that it takes to spec out and build their own. Last year, we helped build Factory 5's new 35 hot rod pickup, which was powered by the Blueprint 306 cubic inch small block Ford. It made 390 horsepower and 370 pound-feet of torque. In keeping with the hot rod theme, triple Strombergs delivered the fuel. We fired it up, synced the carbs, and it ran like a top. Recently, we beefed up a 74 Glencoe jet boat with a Blueprint 540 cubic inch Big Block Chevy. It pulled down 680 horsepower and 669 pound-feet of torque in the dyno cell. Last week, we spent the day at the lake, and it was a face-flapping, rooster-tailing heck of a good time. We can't wait to get this boat back in the water, and we'll be bringing you more of that soon. This 632 cubic inch bullet is coming together for our friends down in XOR. Eliza and Jeremy are working on a classic piece of American off-roading, and it needs some stout horsepower. Let's go down and check it out. What's going on down here?
Hey, what's going on?
Well, I came down to see what this engine is going in. Tell me a little bit about it.
Well, it's a 1963 Willys Wagon, and we want high horsepower to get through the mud. And so we're gonna custom 4-link, probably like 16 inches up, 46s, maybe 54s, 2.5-ton axles. So we're looking to get about 120 miles per hour wheel speed.
Now, I'm not familiar with these type of vehicles. Why does it need that kind of power for this application?
Well, usually most of our vehicles have a lot of gearing, so they don't need a whole lot of horsepower. But since we want to have 120 miles per hour wheel speed to turn the mass of the tires, we need high horsepower.
Now, this thing actually needed some power when it came in because it sounded okay, but I didn't even see what was in it. So
it had a 305 in it. They had already swapped it out because originally these came with a 4-cylinder Hurricane engine, so maybe 100 horsepower?
Maybe. It didn't sound bad. It definitely had the V8 exhaust, but
yes.
It sounded a little on the anemic side, you know.
A little bit. For what we're doing, a little bit, yeah.
Yeah, well, it's okay. So say it made 100, 150 horsepower. It'll roughly have 10 times that now.
That'll be wonderful.
That's what we're shooting for. The engine's going to be good. We're going to crest 1,000 with this. This will be the highest horsepower naturally aspirated engine that we've done. So, and congratulations, you guys get to have it. So.
Thank you. We're excited that you're building us the engine.
Now, I might be stating the obvious, but you don't see a lot of power adders like a blower or a turbo on these type of engines, right?
No, you don't. It's a little too sloppy out for that kind of setup. We don't want any kind of water or mud getting into the system, so that's why you don't see a lot of power adders. So that's why we need big cubic inches and a lot of horsepower.
Well, I think we can help you out because the engine is going to make a lot of power, and if you don't mind, would you come down and help a little bit, maybe torque some stuff on?
Oh yeah, I'd love that.
And you wouldn't want to run the dyno on that, something like that, would you?
No, I wouldn't.
I didn't think so. So when it's ready, we'll come down and let you throw the lever on it. So.
Awesome, I would love that.
All right, we'll get back to work. I'm taking too much of your time.
Have a good one.
Up next, we crank up the compression on the Big Block. Subscribe today to PowerNation Plus and watch all your shows commercial-free.
We're continuing on the buildup of our 632 Big Block Chevy, and for the application down in XOR, we're going to have to make a bunch more power than this engine is currently set up to make, which means we're going to have to change out a few parts. Right now it has a piston that will make 10.8 to 1 compression, which is friendly for pump gas, but for what we're doing, we're going to need a bunch more compression than that, and here's how we're going to get it. We'll be putting in a new set of MAHLE Elite Sportsman Drag Series pistons. Now the big difference with these have a 42cc dome, which will increase our static compression ratio from 10.8 all the way up to 15.36 to 1. Now these have hyper accurate ring lands and lateral gas porting to help improve ring seal, an 043 3mm ring pack, wider pin bosses to help manage the increased inertial loads from these long stroke, high piston speed applications, and also come with an upgraded wrist pin that will withstand heavy nitrous use. All of MAHLE's pistons come ready to run right out of the box with a properly sized wrist pin bore, a dry phosphate coating over the entire piston, and MAHLE's patented Grafal anti-wear coating on the skirt. We're also changing up the connecting rod in this setup, and I'll tell you why in a second. We'll be using a set of Eagle Specialties forged H-beam rods. They're made out of 40-340 steel, have an H-beam design, and are set up for a 990 wrist pin. They are 6/700 in length and have been upgraded with an ARP L19 rod bolt for high horsepower, high RPM applications. We needed the piston that we've chosen for the higher dome volume to get the compression ratio that we want for this application, but it won't work with the rod that came in this engine. That's why we're switching to the Eagle. Here is a quick look how we came up with a calculation of what we needed to use. What we are referring to is block height. The center line of the crankshaft to where the cylinder head bolts on is called block height. In this case, it is 10.200 inches. The piston's compression distance plus the center to center length of the connecting rod plus half the stroke, which is called crank arm, should equal the block height. We tailor the compression distance and rod length with our crankshaft to get that, so theoretically our piston is flat with the deck at TDC. In our case, we have a stroke of 4.750 inches. Divide that by 2, and we have our crank arm, which is 2.375 inches. Add the connecting rod center to center distance, which is 6.700 inches, as well as the 1.120 inches piston compression distance, and we have a total length of 10.195 inches. If our engine's deck height is truly 10.200 inches, and we subtract the 10.195, we can determine that our piston is 5/1000ths of an inch in the hole. Of course, we have to physically measure the deck height to see if that's correct. The first step is to put a rod and piston assembly together for mock-up. After removing the current piston and rod combination, we'll drop our mock-up setup into place. Then we'll run the piston up to top dead center, checking it with a dial indicator. Then we rock the piston back and forth, finding the highest and lowest point in the bore at TDC. The average of those two measurements tells us how far the piston is in the hole. In our case, it's 8.5 This is one of the measurements that we do use to calculate final compression ratio for the combination. And this number also affects other things in the engine. But for right now, we have this number and we can get the rest of the rods and pistons put together. When putting together our piston and rod assemblies, we like to use Permatex Ultra Slick Engine Assembly Lube. This specially formulated lubricant protects components from excessive friction and wear during initial engine startup. Because the wrist pin's bore intersects the ring land on the oil ring, we're going to have to run a support rail, and it is held in place by this mark that keeps it from rotating. It supports the oil ring to keep it from burning excessive oil. We're using the Goodson Power Ring Filer to gap the rings. This second compression ring is being gapped to 28/1000ths. A fine stone is used to deburr the edge. With the ring installed, a Summit adjustable ring squaring tool gets it perfectly into position, and a feeler gauge is used to check the gap. We're going to be using an upgraded ring pack in this operation because of the amount of horsepower it's going to make. It still has a standard tension oil ring to control the oil and a Napier style second ring which has a small hook on the edge that will actively scrape oil off the cylinder. The top is the special one. It is an uncoated steel nitride ring which will hold its tension better than a standard ductile ring.
Our quest for power continues with an aggressive cam and a heavy-duty belt drive. Subscribe today to PowerNation Plus and watch all your shows commercial-free.
Welcome back to Engine Power. We're building a 632 cubic inch Chevy Big Block that's going to go into a 63 Willys wagon down in the XOR shop. Once the pistons are in, we can torque up the rods. The most accurate way to do this is using a rod bolt stretch gauge. This tool measures how much the bolt stretches under a specific torque load. The spec for this L19 rod bolt is 73 to 77 10/1000ths. The goal is to tighten the fastener until it reaches its maximum clamping force, without over-tightening the bolt until it becomes distorted or compromised. In fact, whenever you're tightening a fastener to a torque spec, what you're really doing is stretching the fastener to the ideal length under load, which on most fasteners is 75% of its yield. For the ultimate in accuracy and adjustment, we're installing a Jesel belt drive system. It comes with a billet aluminum cover that's O-ringed for a leak-proof seal. Next, the camshaft gently slides into the block. This is an off-the-shelf solid roller offering from Comp Cams. The specs are impressive by any standards. Duration at 50 thousandths lift on the intake is 285 degrees and 300 degrees on the exhaust. Lobe separation angle is 114 degrees. Gross valve lift on the intake side with a 1.8 rocker is 873 thousandths and 848 thousandths on the exhaust. The thrust washer gets installed on the camshaft adapter provided by Jesel. Then it's wiped completely dry with lacquer thinner to remove any trace of oil. Next, a thin but thorough layer of silicone covers the thrust shim before it's put in place. The camshaft thrust plate slides in and is torqued to 96 pound-inches or 8 pound-feet. The crank gear is seated into place. Then the belt and the cam gear are installed and torqued to 70 pound-feet. As always, we degree the camshaft. This allows the engine to make the most power where we want it. The intake center line comes in at 113.5, which is a ½ degree advanced. And that is within a ½ degree of straight up, meaning the camshaft's intake center line is the same as its lobe separation angle. Now we don't plan on moving the cam around a lot because we want the engine to make power in a specific place in the RPM range. So we are going to check our piston to valve clearance with the camshaft in this position. Our solid roller lifters are from Comp Cam's premium Sportsman series. Even though this is only mock-up, we'll be certain to use the correct thickness head gasket. New gaskets will go on for final assembly. Once the head is set into place, we'll drop in a few ARP studs to keep it there. We need to check for push rod length. So to do this, we'll drop in a couple of adjustable push rods. We'll set the adjuster on our Jesel rocker arms to 1 full turn of adjustment. Then we'll lengthen the adjustable push rod while the cam is on base circle until we have the correct lash, which is 24 thousandths on the intake and 26 thousandths on the exhaust. We'll set up our dial indicator to check piston to valve clearance. The intake is checked at 10 degrees after TDC on split overlap. We zero out the indicator and press down until the valve contacts the piston. We have a roomy 100 thousandths clearance. We'll do the same for the exhaust valve, but it's checked at 10 degrees before TDC on split overlap. The result? A whopping 135 thousandths. In other words, this thing has a ton of clearance.
Up next, high-flowing heads for our bullet.
Now the studs will help so you can align it.
Subscribe today to PowerNation Plus and watch all your shows commercial-free.
Welcome back, and we're continuing on our 632 buildup. And next to go on is an ATI super damper we picked up from Summit Racing. Since everything is torqued up and ready to go, we'll install our Melling high volume oil pump and our new 7-quart pan. To make the power we want to make, we need a lot of airflow. So we called up Summit Racing and got a set of AFR 385cc rectangle Magnum 24-degree Big Block Chevy heads. There's nothing small about these. They have a 2 350 intake valve, 1 880 exhaust on a 121cc chamber, so they take a minimum of a 4 250 bore. Now the 385 refers to the intake port size, which is 385 cc's. Now that will flow a massive 452 CFM at 800 lift. It also has a 135 cc exhaust port, which flows at 344 CFM at that same lift. They are set up with a 1/625 OD spring, which is good for 850 lift, which is right in the range of our cam. These heads will make big power on a big engine. Because this bullet is going in the Willys project in XOR, I thought it'd be a great idea to have Eliza and Jeremy down to help torque up the heads. All right, that one's for you. Now the studs will help, so you can align it. Keep this on the bottom right there. There you go. And right on the dowels.
Ooh, those are pretty.
All right. Studs are next. The reason we do studs first, down here just for guide, and then later because we don't want to drag a head over a bunch of installed studs because it'll drag some aluminum in it. So.
Oh, and you're still letting us run the dyno on this, right?
Yes. If you get a little crazy in the dyno, you can wound it. So, but we'll keep you out of the woods.
Just tell me what buttons to push.
Tell me what buttons to push.
That big lever, I'm just gonna push that forward.
First click.
Okay.
Makes you a little scared sometimes when you got to pull on them.
Yeah. Now, once you've torqued several thousand of these, you're gonna get used to it. I know it seems kind of complicated, but it's not. You're just going in a circle.
Do you always turn your torque wrenches back out?
Absolutely. On a click type, always return it to 0. So.
Perfect. Well, I'm going to turn this one back out, and that gives us a point to also get out of here and let you finish putting this back together.
Okay, I'll take that
Take
from
care
you.
of our baby.
Nice job, and I'll have you back down for the next part, which is probably going to be
the dyno pulse.
On the dyno. So.
Sounds great.
All right, good job. For more information on anything you've seen on today's show, visit PowerNationTV.com. When building any engine, one of the most important factors to consider is compression ratio. Now, the parts that you choose for your build are designed to achieve a specific compression ratio, but that is totally dependent on what you're doing. Now, simply put, compression ratio is the maximum volume of the cylinder divided by the minimum volume of the cylinder, or another way of putting it, the volume of the cylinder at BDC divided by the volume of the cylinder at TDC. And what makes compression ratio so important? It directly affects the power level and operating range of a given engine application. Generally speaking, the higher the compression ratio of the engine, the higher the potential power output. Higher octane fuels are required for most high compression engines to achieve optimum power output. Strictly speaking, static compression ratio measures volume only, not pressure. There are high compression, low cylinder pressure engines that are designed primarily for fuel efficiency and not just outright power. In our world, we want to generate as much cylinder pressure as possible to increase power. Higher static compression makes this easier to achieve. On the other end, there are actually low static compression but high cylinder pressure engines that also require high octane fuel, but that involves something called dynamic compression ratio, and that's a topic we'll get into later on in depth. These engines are typically purpose-built race bullets that have to conform to very specific compression rules but still make big power. There are 5 variables that affect compression ratio, and changing any one of these factors will raise or lower it, and we're talking about volume. They are, number 1, the swept volume of the cylinder. If you change the bore or stroke of a cylinder, you will change the volume of that cylinder and therefore its compression ratio. Number 2, combustion chamber size. Increasing it will lower the compression ratio, and decreasing it will raise the compression ratio, assuming that no other changes have been made. Number 3, head gasket volume, meaning the gasket's bore size and the gasket's thickness. You might not realize it, but the variations in head gasket volume can increase or decrease compression ratio by over a half a point. Number 4, the volume of the cylinder at TDC with no other components. In most engines, the piston stops just shy of being level with the deck of the engine block. This small volume of additional space lowers the static compression of the engine slightly. Number 5, piston volume. A dome-shaped piston takes away volume, increasing static compression. A dish-shaped piston adds volume, therefore decreasing compression.
Now you know the 5 factors that determine engine compression ratio. You can use this info to more carefully plan your future engine builds. Next time, we'll show you how to measure and calculate the static compression ratio in your project vehicle.